Day 97 Notes, Advanced Algebra 2. Today we continue our discussion with functions and we identify domain and range of function equations. Sometimes we don't need to find the domain and range of functions when they're given to us as numeric values, but instead we need to find the domain and the range of functions when they're given to us as an expression like this. And so what I would encourage you to do when we initially start discussing this type of problem, when we're looking for the domain and range, is start with the domain value and consider what are some of the x values that I can put in place of all of our variables here, and is that going to cause a problem for our calculation? So for example, let's start just somewhere close to the center of what a graph would be and pick an x value of 0. Can I put an x value of 0 into this equation? And the answer would be yes, 0 works. So maybe I'll write that down and check it here. What about something like a -5 or a -1 or a -2? Could I put a negative number into this calculation and get a result? And again, the answer is yes. There's nothing wrong with changing these letters x into the number -5. Well, what about the number +5? Would that be okay too? And surely you would find that it is. We can use the number 5. We can use the number 10 and 15 and 20. Any of these values will work. In fact, if we provide you with a polynomial altogether, you'll find that there are no x values that cannot be calculated in this expression. And hopefully that makes sense to you, because you'll remember that polynomials are what we call smooth and continuous. At least the graphs of a polynomial are smooth and continuous. And since they are smooth and continuous, continuous is the big term that we're going to use here, we can draw a polynomial without picking up our pencil. We can draw from one side of the polynomial to the other without picking up our pencil. And if we wanted to travel towards positive infinity in the x direction and negative infinity in our y direction, we could do that. There is no limit to the x values that we choose. So if I were going to write the answer for my domain using set builder notation, I might write something like this. The domain is the set of all x values such that x is an element of the real numbers. X is allowed to be any number that's part of the real number system. So if I wrote this in full set notation, that's what my answer would look like. If I allow the abbreviated form, then it would be something like this. X has to be an element of the real numbers. And that would be a good answer for our domain. As far as our range goes, let's consider what happens when we start picking big and bigger numbers and then smaller and smaller numbers. What happens to this polynomial as we pick values that are getting bigger and bigger and bigger? For example, I know that I can pick any x value as long as it's a real number. So let's pick a really big real number. What happens here? Well, the function gets bigger and bigger and bigger. If I picked 1,000, for example, 1,000 cubed minus 4 times 1,000 squared minus 15 times 1,000 plus 8, that's going to be a really, really big number. And the same thing's true when I pick a number like a -1,000. That's going to be really, really small. In fact, I don't have to think about the mathematics at all or the calculations behind it whatsoever, because I know the end behavior of this function. Remember, the end behavior said that if this has a positive leading coefficient and an exponent of 3, its tail has to be pointing up like this, and anything in the middle can be whatever. It doesn't make a whole lot of difference to us, because right now we're talking about the range values or the acceptable y values for the coordinates that fit on this graph. And this should be enough to prove to you, or at least enough to convince you, that for the y values I can pick any number again as long as it's an element of the real numbers. Y is an element of the real numbers as well. Again, I can go along this graph in any direction, either way out to the right or way out to the left, and eventually I will find a coordinate who has a y value anywhere in the real number system. And so that's kind of interesting. With a polynomial, and this is true for any polynomial for that matter, its domain will be any real number, and its range will also be any real number. Well, let's look at a radical equation for just a moment. This one's just slightly different when I start considering my domain values. Well, let's start with 0 right off the bat, like we did a moment ago. Can 0 be used in this calculation? Well, if I put 0 in place of x, that would be 0 minus 4. And can I find the square root of negative 4? Well, yes and no. The square root of negative 4, we know it's supposed to be 2I, but this is an imaginary solution. I, as an imaginary solution, will not show up on a graph of a Cartesian coordinate grid. It does not show up in our traditional graphing sense when we look at graphs like this. So truthfully, can I use x in my domain? The answer would be no, because it is not, or it will not produce an answer that's a real number. So x is off the table, or I'm sorry, 0 is off the table. We can't use 0. Could we use 1? Well, no, again, we can't, because we'll run into the same problem. 1 minus 4 is a negative number. We can't take its square root. How about 2? 2 won't work. How about 3? That's not going to work. But what about 4? Is 4 going to be okay? Well, at this point, you can say yes, because 4 minus 4 is 0, and the square root of 0 is 0. That's a real number. That's a value that we can calculate. So for our domain values, x can be 4. Can it be 5? Sure. Can it be 6? You bet. It can be any number bigger than 4, but nothing below 4 seemed to work. In fact, even if I went further backwards and tried negative 1, again, you should see that that doesn't work either. Negative 1 minus 4 is negative 5. How about negative 2? Again, no good. We're moving smaller and smaller. We're making more negative numbers. But it does look like anything bigger than 4, or I should say anything 4 or bigger is okay. So when we go to answer our domain results, we can say that x can be any number as long as x is greater than or equal to 4. Now, what can we do about the range? What values can y be in our range? Well, the way I would answer this is I would look at the smallest domain value and see what happens to our range at that point. When x is 4, that seemed to be where our cutoff was, our calculated result was 0. So our range became the number 0. Input was 4, output was 0, domain turned into range. And when we started moving to the right, when we started moving further into our domain, then our range value became bigger and bigger. Now, 5 minus 4 is 1, so the square root of 1 is 1. So the input of 5 becomes the output 1. And I could be drawing a mapping diagram here if I wanted to. Input 4, output 0. Input 5, output 1. Input 6, well, 6 minus 2, or 6 minus 4 is 2, and the square root of 2 is kind of hard to calculate. Let's jump up to the input 9. Input 9, oops, no, that's not going to work either. Let's say input value of 8, because 8 minus 4 is 4, and the square root of 4 is 2. We have an input of 8 and an output of 2. These domain values over here are again steadily increasing. It looks to me like 0 is the smallest number, and so as long as y is greater than or equal to 0, then it can be a number in our range. These radical equations start to produce these domain and ranges that are a bit interesting. You'll notice that the domain has a low point. There are no numbers less than this 4 in this case, and there are no numbers less than 0 in our range. So this radical equation just seems to cut off part of our domain and part of our range. A rational expression is different yet still. Rational functions are nothing more than polynomials written as a fraction. And we said a moment ago that polynomials are allowed to use any domain value. We can use all real numbers for our domain and all real numbers for our range. However, when we look at a rational function, we encounter a problem because while any input value can be used for our numerator, we're not allowed to use at least one number in our denominator here because I don't want to allow this denominator to become equal to 0. And if we look carefully, this 3x plus 3 could equal 0 when, and let's do the math here, let's subtract 3 from both sides, then divide by 3, that's going to be a -1. When x is equal to -1, that's going to make our denominator equal to 0, and that's a problem. So back to our domain, this operates, or this is very similar to a polynomial in that we can use any x value for most of the time, but x cannot be equal to -1. X cannot be equal to -1 because that would create a 0 in the denominator, and that is a problem. As far as our range goes, however, we can look to the left and to the right anywhere in the graph of this function, and that will produce an output value. So y can be an element of any real number when it comes to the range. We can pick or we can find any y value in the real number system in a graph like this. Now, talking about equations and finding domain and range inside of equations is a difficult thing without looking at a graph. So let's take some time to look at the graphs of a few of these equations because they definitely can help. And some of the questions that you have to ask yourself based on our inspections of polynomials and radical functions and rational functions is, when you're considering the domain, does the graph stop to the left or to the right? Is there a limit as far as how far the graph can move to the left or to the right? That will help you answer questions about the domain. And then another question might be, is there a maximum or a minimum value? That would help you answer some questions about our range. We can find maximums and minimums using our calculator, and we can look for holes or gaps in our graph by using our calculator as well. So let's go back and take a look at these three functions again, and we'll decide whether or not this domain and range starts to make a little bit more sense by looking at the graphs. So let's start with this first one here. Going to the graphing calculator, we have x cubed. Oops. Let's try this again. X to the third power minus 4x squared minus 15x plus 18. And here's an equation of the graph. It's a little bit tough to see right now, so if we start zooming out, a little bit, we can start to see the behavior of this graph. Clearly, the range values go from -infinity to +infinity. We can pick a y value as small as we want and find it on this graph. We can pick a y value as big as we want and we can find it on the graph. What's not so obvious is that our x values, we can do the same thing as well. It doesn't look like our x values are moving to the right very much at all, but they really are. They are continuing to move to the right, just not quite as fast as the graph is moving up or down. So really, if I wanted to pick a very, very small x value, I can do that. I can move very far to the left. I'd have to move awfully far down the function down below, but I could do that. I could move to the left as far as I want and find a point on this blue graph, and I can move to the right as far as I want, and I can find a point on the blue graph as well. This picture should be enough evidence to convince you that yes, the domain is any real number, and the range is also any real number. Let's see what happened with our radical function here, the square root of x minus 4. So I'll press the Tab key and clear this equation. And let's write the square root of x minus 4. And we'll press enter here. What I'd like to do is zoom in a little bit, and we'll take a look at what this graph tends to look like. Here we are zoomed in pretty far, and I'll shift it over here. The smallest x value that we encounter, let's see, this is in units of 0.5. There we go. That's a little bit easier to read. These tick marks now represent units of 1. So the smallest x value that we see in this graph, it looks like it's coming from the right, and then it all of a sudden stops here. The smallest x value that we're allowed to have is this one right here, and that's at 1, 2, 3, 4. We just said that a moment ago, that x can be as small as 4, but x must be greater than that. Okay, it can be as small as 4, but it also must be greater than 4. We can't pick any x values that are smaller than that. Now, similarly, if I'm thinking of the coordinates along this graph, none of those coordinates will have a y value that are smaller than 0. Again, it seems to be coming in from the right here, and then it all of a sudden stops. I can't find any y values that are smaller than this. And if I were to zoom out, here, you'll notice that this graph doesn't get any smaller. There's no way that it curves back down. There is no point where the y value gets to be smaller than 0. And that's what we were saying here with these two solutions. The x value has to be bigger than 4, bigger than or equal to 4, and the y value has to be bigger than or equal to 0. This radical graph creates this shape here, and it limits our domain and range. It sort of just gives us the stopping point to which we can no longer move left or right. Let's look at this last equation, x squared plus 2x over 3x plus 3. So we'll clear this one out, create a fraction. I want x squared, whoops, there we go, x squared plus 2x over 3x plus 3. And we'll press enter here. This graph does something interesting. It splits itself into two parts. We have a lower portion down here with this curve, and then an upper portion here with that curve. And you'll notice that with any x value that I choose, either big or small, I can find a coordinate on the graph associated to that x value, except for this one here, except for when x is equal to -1. The graph tends to split apart and it diverges away from itself. And if I were to pick different x values and calculate them into this function, I can calculate them all except for when x is equal to -1. And let me show you what I mean here. If I picked x equal to 0, my y value is equal to 0. And if I picked x equal to +1, my y value is going to be 1/2, or 0.5. If I picked -2, I could find a calculation. That comes out to be 0. And if I picked -3 for x, I can get a calculation there as well, -0.5. However, watch what happens when I input the value of -1. We get this vertical line that's dotted here, and my answer, my end result, comes out to be undefined. And I think that should make sense to you. We've talked a little bit about this before already, that we can't divide by 0. We get an undefined result. But that picture of that dotted line is something that's new. That's what we call an asymptote, and those are created when we encounter holes or gaps in our graph like this. So the term is called asymptote, and there might be more than one, so we'll say asymptotes. But this is the portion of a graph where an equation or the graph of an equation will approach a line, but it will never touch or cross that line. And that's what we would also call a gap in the graph. We'll talk more about these tomorrow in class. I have some sample problems that I'd like for you to work on. In the meantime, please let me know if you have any questions with them, and we can talk about them tomorrow in class.